Welcome to Study Session 8. Introduction. The first issue of the Institute's Health Emotions newsletter, published in 2000, noted, "Understanding how the brain experiences emotion and how positive states of mind influence the body is part of the next great frontier in the brain sciences. It is the life science equivalent of discovering the fundamental particles that constitute the building blocks of matter in physics." Jack Thompson, professor in the Department of Psychology and Psychobiology at Center College, Danville, and author of the Psychobiology of Emotions, pointed out that humans have taken the long route in the pursuit of an anatomically and physiologically accurate explanation for their emotions. He pointed to the long era of misinformation that preceded modern knowledge. Egyptian physicians believed that the heart was the site of consciousness, he said. They had no concept that the brain was associated with feeling, thinking, or other functions. For them, the brains were for eating. It wasn't until the Greco-Roman period that the notion of the brain's connection with thought and feeling was introduced. But even then, the idea that the heart was the seat of passionate emotions persisted. The neurobiology of love has been a difficult topic to approach, Thompson conceded. No one has yet been able to tackle and fully explain it. This study session introduces you to biology of emotion. Learning outcomes. At the end of this study session, you should be able to 1. Highlight the biology of emotion. 2. Identify the nervous system and explain. 3. Discuss the measurement of emotion. Biology of emotion. Emotions are often experienced directly in the body. When strolling through the park to meet with your sweetheart, you walk lightly with your heart pounding with excitement, whereas anxiety might tighten your muscles and make your hands sweat and tremble before an important job interview. Numerous studies have established that emotion systems prepare us to meet challenges encountered in the environment by adjusting the activation of cardiovascular, skeletal muscular, neuroendocrine, and autonomic nervous system. This link between emotions and bodily states is also reflected in the way we speak of the emotions. A young bride getting married next week may suddenly have cold feet. Severely disappointed lovers may be heartbroken, and our favorite song may send a shiver down our spine. Both classic and more recent models of emotional processing assume that subjective emotional feelings are triggered by the perception of emotion-related bodily states that reflect changes in the skeletal muscular, neuroendocrine, autonomic nervous systems. Nervous system. These conscious feelings help the individuals to voluntarily fine-tune their behavior to better match the challenges of the environment. Although the emotions are associated with a broad range of physiological changes, it is still hotly debated whether the bodily changes associated with different emotions are specific enough to serve as the basis for discrete emotional feelings such as anger, fear, or happiness, and the topographical distribution of the emotion-related bodily sensations have remained unknown. The experience of emotion is accompanied by activation of two major areas of the nervous system, the brain and the autonomic nervous system. Activation of brain regions. The area of the brain known as the limbic system is highly involved in emotion. One structure in the limbic system, called the amygdala, plays a particularly important role in regulating emotion. Researchers believe that sensory information about emotion-evoking events move along two pathways to the brain. The information goes first to the thalamus and from there moves simultaneously to the amygdala and the cortex of the brain. The amygdala processes the information quickly and sends signals to the hypothalamus, which in turn activates the autonomic nervous system. The cortex, on the other hand, processes the information more slowly, allowing people to appraise or evaluate the event. Example: when information travels from the sense organs to the thalamus to the amygdala, people respond instantaneously without thinking to events in their environment. A parent may snatch a child away from a curb without thinking if she hears the sound of squealing tires coming towards them. Defined as such, these emotional states are specific manifestations of non-verbally expressed feelings of agreement, amusement, anger, certainty, control, disagreement, disgust, disliking, embarrassment, fear, guilt, happiness, hate, interest, liking, love, sadness, shame, surprise, and uncertainty. If distinguished from reactive responses of reptiles, emotions will then be mammalian elaborations of general vertebrate arousal patterns in which neurochemicals, for example, dopamine, noradrenaline, step up or step down the brain's activity level, as visible in body movements, gestures, and postures. In mammals, primates, and human beings, feelings are displayed as emotion cues. More recent research has shown that some of these limbic structures are not as directly related to emotion as others, while some non-limbic structures have been found to be of greater emotional relevance. The following brain structures are currently thought to be the most involved in emotion. 1. The amygdala. The amygdala are two small round structures located anterior to the hippocampus near the temporal poles. The amygdala are involved in detecting and learning what parts of our surroundings are important and have emotional significance. They are critical for the production of emotions, particularly for negative emotions, especially fear. The damage to the amygdala results in an inability to appropriately process fear. Animals with damaged amygdalas cannot develop conditioned fear responses. People with damaged amygdalas can't recognize fear in other people, though they may be able to experience fear themselves. 2. Prefrontal cortex. The term prefrontal cortex refers to the very front of the brain, behind the forehead and above the eyes. It appears to play a critical role in the regulation of emotion and behavior by anticipating the consequences of our actions. The prefrontal cortex may play an important role in delayed gratification by maintaining emotions over time and organizing behavior towards some specific goals. 3. Anterior cingulate. The anterior cingulate cortex, ACC, is located in the middle of the brain, just behind the prefrontal cortex. The ACC is thought to play a central role in attention and may be particularly important with regard to conscious, subjective, emotional awareness. This region of the brain may also play an important role in the initiation of motivated behavior. 4. Ventral striatum. The ventral striatum is a group of subcortical structures thought to play an important role in emotion and behavior. One part of the ventral striatum, called the nucleus accumbens, is thought to be involved in the experience of goal-directed positive emotion. Individuals with addictions experience increased activity in this area when they encounter the object of their addiction. 5. Insula. The insular cortex is thought to play a critical role in the bodily experience of emotion, as it is connected to the other brain structures that regulate the body's autonomic structures: heart rate, breathing, digestion, and so on. This region also processes taste information and is thought to play an important role in experiencing the emotion of disgust. Autonomic nervous system. The autonomic nervous system controls all the autonomic functions in the body. When an emotion-evoking event happens, the sympathetic branch of the autonomic system, which prepares the body for action, begins to work. It sends signals to the adrenal gland, which secretes the hormones epinephrine and norepinephrine. These hormones in turn prepare a person to face the challenges of the event. The following physical responses are indicative in a man or woman: blood pressure, heart rate, respiration rate, and blood sugar levels increase and prepare a person for action. Pupils dilate to let in more light for vision. The digestive processes slow down so that energy can be directed to the crisis at hand. The autonomic nervous system is made up of two parts: the sympathetic and parasympathetic nervous system. Unlike the sympathetic nervous system, which prepares the body for action, the parasympathetic nervous system keeps the body still. The sympathetic nervous system involves expending energy, while the parasympathetic nervous system works to keep energy in the body. Somatic marker theory of Damasio, 1990, is based on the study of Elliot. The brain synthesizes a wide variety of information that is obtained by the body to produce a unified concept, that is, emotional state. The association between an emotional state and bodily changes equals somatic marker. Somatic markers are used to make decisions. However, when the frontal lobe is damaged, it may result in A, inability to access acquired somatic markers, or B, inability to use information provided by the somatic markers. Measuring emotion. Researchers often use autonomic responses to measure emotion. One frequently used autonomic response is called the galvanic skin response. The galvanic skin response is an increase in the skin's rate of electrical conductivity, which occurs when subjects sweat during emotional states. Researchers also use indicators such as blood pressure, muscle tension, heart rate, and respiration rate to measure emotion. Polygraph tests. The polygraph, or lie detector, is a device used to detect deception. In reality, the polygraph cannot detect deception. Instead, it measures autonomic indices of emotion. A subject is hooked up to the device and asked a series of neutral questions such as, "What is your name? Where do you live?" and so on. The polygraph records the autonomic responses as the subject answers these questions, establishing the baseline or normal pattern of autonomic activation. Then the subject answers other questions that can determine guilt or innocence, such as, "Where were you in the night of the murder?" In theory, when lying, the subject feels emotions such as the nervousness or anxiety, and the polygraph records accompanying changes in autonomic activation. In practice, the polygraph is not very effective. Polygraph tests have a high error rate for two main reasons. Many people who are not engaged in deception feel nervous or anxious when asked questions concerning their guilt or innocence. People who are engaged in deception can often trick the polygraph by acting tense during neutral questions, so that their baseline responses resemble their responses during the critical period of questioning. Summary of study session. 1. The brain is the powerhouse of emotion. No emotion could be manifested without the brain involvement. In the regulation of emotion, both limbic and non-limbic systems have something to do with how emotions are regulated. More recent research has shown that some of these limbic structures are not as directly related to emotion as others, while some non-limbic structures have been found to be of greater emotional relevance. The following brain structures are currently thought to be most involved in emotion. These include the amygdala, prefrontal cortex, anterior cingulate, ventral striatum, and the insula. 2. Also, autonomic nervous system consists of sympathetic and parasympathetic nerves. The autonomic nervous system controls all the automatic functions of the body. The lecture also stressed the relevance of polygraph in measurement of emotion. 3. The galvanic skin response is an increase in the skin's rate of electrical conductivity, which occurs when subjects sweat during emotional states. Researchers also use indicators such as blood pressure, muscle tension, heart rate, and respiration rate to measure emotion. We have come to the end of study session 8. Thank you.